There's a photograph sitting in an archive that was taken on June 21st, 2025, 10 full days before a single human being on Earth knew what it was looking at. No telescope has ever accidentally photographed an interstellar visitor before its own discovery. No object crossing our solar system has ever carried a chemical fingerprint this old. No comet in the recorded history of astronomy has been confirmed independently by two of the most powerful instruments ever built, telling the exact same impossible story. It is not a warning shot fired across our solar system. It is a fossil moving at 60 kilometers every single second, and it is real. Stay with me, because the last piece of this story was only confirmed a few weeks ago, and it changes what scientists now believe this object actually is. If you're new here, this channel breaks down real space discoveries the moment the data confirms them. No speculation dressed up as fact. So if that's your kind of thing, subscribe now, because you're going to want to see where this goes. Let us go back to the beginning. On July 1st, 2025, the Atlas Survey, a NASA-funded network of robotic telescopes built specifically to scan the sky for fast-moving objects, picked up something near the constellation Sagittarius that didn't behave like anything in its catalog. Most objects astronomers track are asteroids and comets bound to the sun, looping around on predictable elliptical paths that repeat for centuries. This one wasn't looping. It was moving on a hyperbolic trajectory, a path so fast and so open that the sun's gravity could never pull it into orbit, meaning it came from somewhere outside our solar system entirely, and was simply passing through, once, forever. That distinction matters enormously, because in the entire history of astronomy, this has only happened twice before. The first confirmed interstellar visitor, Oumuamua, was spotted in 2017, tumbling and strange with almost no gas or dust around it. The second, 2I Borisov, arrived in 2019, behaving much more like a familiar, ordinary comet. Both were gone within months, and by the time telescopes turned to study them properly, the best data was already slipping away. Astronomers had spent years afterward wishing they'd had more warning, more instruments, more time. This new object, officially designated 3I Atlas, the third confirmed interstellar object ever recorded, was going to be different and not by accident. It arrived just as two of the most capable observatories in human history were coming online. Here's why the old caution made sense. For decades, astronomers assumed interstellar objects had to be exceedingly rare, simply because none had ever been detected. And building a case for spending billions of dollars on telescopes designed partly to catch objects nobody had ever actually seen was a hard sell. The math said they should exist. Every star system that ever formed planets should have flung leftover debris out into the galaxy over billions of years by the trillions, but until 2017, that math was theoretical. Oumuamua changed the argument overnight, and by the time 3I Atlas turned up 8 years later, the scientific community wasn't scrambling to justify the search anymore. It was already building the tools, chief among them, the Vera C. Rubin Observatory, a new NSF-DOE facility in Chile, carrying the largest digital camera ever built for astronomy, designed to photograph the entire visible southern sky every few nights for 10 straight years, cataloging anything that moves. Rubin wasn't even fully operational yet. It was still in a testing phase called science validation, calibrating its instruments before its main survey formally began, and that timing turned out to matter more than anyone could have planned. It's worth understanding just how narrow the window for catching an object like this really is. Interstellar visitors don't announce themselves months in advance the way a returning comet does. They arrive on hyperbolic trajectories at tremendous speed, are typically faint and small until they're already inside the orbit of Jupiter or closer, and give astronomers, at best, a matter of months before they fade back into the dark permanently. Every hour spent confirming what an object even is, before serious observation time can be allocated, is an hour of irreplaceable data lost. That's precisely why the accidental timing of Rubin's very first calibration images turned out to matter so much. Not because anyone planned it, but because a telescope built to eventually scan the entire sky happened to already be pointed in the right direction for entirely unrelated reasons in the days before anyone knew there was anything there to see. Here's the number that changes everything about this story. 10. 10 days. That's how long before its official discovery that 3I Atlas was already sitting, unnoticed, inside Rubin Observatory's test data. On the very first night of Rubin's Science Validation Survey, June 20th, 2025, the telescope happened to sweep across the small patch of sky where the object was quietly approaching, and it captured the object's light without anyone realizing what they had. 10 days is nothing on a cosmic scale, less time than it takes most people to notice a new pothole on their commute. But on the scale of tracking an object moving through interstellar space at roughly 221,000 kilometers per hour, 10 extra days of positional data is enormous. Read that again. A machine photographed an interstellar object before humanity even knew it existed. When astronomers at the LSST Interdisciplinary Network went back through Rubin's commissioning images after the official announcement, they didn't just confirm the object was there. They extended its known observation history backward by more than a week, refining its orbit with a precision no single night of data could have provided. This is the delayed reveal at the heart of the whole story. The discovery everyone celebrated on July 1st had, in a very real sense, already happened, unread, in a hard drive in Chile. Then Hubble stepped in July and August of 2025, delivering the first real-size estimate, a nucleus somewhere between roughly half a kilometer and just over 5.5 kilometers across, a range wide enough that scientists knew immediately they'd need better data to narrow it down. Translate that range to something concrete. Even at its smallest plausible size, the solid core of this object is bigger than most city downtowns, moving through space at a speed that would cross the continental United States in about 20 minutes. Later, after the comet's closest approach to the Sun had passed, refined observations separating the faint glow of the solid nucleus from the much brighter surrounding coma settled on a more precise figure, an effective diameter of about 6 kilometers, give or take roughly 400 meters, meaning this single icy body is, by mass, on the order of 1,000 times heavier than the previous interstellar visitor, 2I Borisov, and roughly 1,000,000 times heavier than Oumuamua. And unlike Oumuamua, which showed almost no visible activity at all, 3I Atlas behaved exactly like a classic active comet, a genuine coma of gas and dust, a tail, all the visible hallmarks scientists expected. Except its chemistry wasn't behaving like anything nearby. Spectral readings, including early looks from the James Webb Space Telescope in August 2025, revealed something scientists hadn't seen in this proportion before. The comet was unusually rich in carbon dioxide relative to water vapor, a ratio distinct from the vast majority of comets native to our own solar system, where water almost always dominates the outgassing. Here's where it gets worse before it gets clearer. A comet's ice chemistry is essentially a chemical time capsule, locked in from the moment it formed around its parent star. If this object's ice doesn't match our solar system's chemical recipe, that's not a glitch in the data. That's a direct chemical signature of a completely different stellar nursery, sealed shut for longer than most stars in the sky have existed. Here is where this stops being abstract. Every comet we've ever studied up close, Halley, Hale-Bopp, the dozens NASA and ES emissions have sampled or flown past, formed alongside our own sun, out of the same disk of gas and dust that built Earth, Mars, and everything else in the solar system. They are, in a real sense, family. 3I Atlas is not family. It is a physical sample of chemistry from an entirely different corner of the galaxy, delivered to our doorstep for free, without us having to build a single spacecraft to go get it. Every gram of ice this object sheds as it passes. The Sun is a direct laboratory sample of what planetary systems look like somewhere we will never travel to in a human lifetime. Think about what that actually means for the field of planetary science as a whole. For the entire history of the discipline, everything we've learned about how planets form has come from studying one single example, our own solar system, and extrapolating outward. An object like this is the first real chance to check that extrapolation against physical evidence from somewhere else. This is, quite literally, the closest humanity has ever come to touching another star system's leftovers with our own instruments. No mission proposal, no decade-long journey, no funding fight. It arrived on its own, and all we had to do was be ready to look. The object's trajectory carried it almost directly behind the Sun during its closest approach, meaning that at exactly the moment its solar heating, and therefore its most dramatic activity, would peak, it would also become completely unobservable from Earth. The comet passed behind the Sun in October 2025 and simply vanished from every ground-based telescope on the planet. For astronomers, this was close to a nightmare. The single most scientifically valuable window of the entire flyby, the moment of perihelion itself, was going to happen with nobody on Earth able to watch it directly. So the global astronomy community did something remarkable. They organized. The International Asteroid Warning Network launched a coordinated observation campaign running from late November 2025 into late January 2026, pulling together data from every instrument that could get any kind of angle on the object. Spacecraft near Mars. For a few tense weeks in late 2025, that discrepancy became a genuine point of scientific debate. Was this ordinary, if vigorous, cometary evaporation, or was something else going on that the models weren't capturing? Every telescope pointed anywhere near the comet's expected position became, briefly, part of an anxious waiting game. Measure, wait, recalculate, wait again, with nobody able to simply look directly at the one place that actually mattered until the geometry of the solar system allowed it. Then, on October 31st, 2025, astrometric observations resumed as the comet finally cleared the Sun's glare. It had survived. Sequential imaging showed the nucleus intact. No catastrophic breakup, No scattered debris field where a comet used to be. Just a comet, battered by its closest approach, but structurally whole, continuing on exactly the retrograde, outbound path its orbit had predicted before it ever went dark. Within weeks, additional post-perihelion data from the Minor Planet Center and NASA's Jet Propulsion Laboratory refined the non-gravitational acceleration measurement, and NASA's own analysis concluded what mission scientists had suspected from the start. The observed perturbations were small and consistent with ordinary outgassing as the comet's ices sublimated in sunlight, the same physical process that nudges the paths of countless solar system comets every single orbit. With the danger of a hidden, unobserved perihelion behind them, astronomers spent the winter and spring watching 3I Atlas complete its swing through the inner solar system and head back out the way it came. Its closest approach to Earth itself had actually already happened weeks earlier, on December 19, 2025, at a distance of about 8 astronomical units, roughly 270 million kilometers, more than 700 times farther away than the Moon, and NASA has been explicit and consistent on this point throughout. There has never been any collision risk, and the object's path was always going to carry it safely past Earth on its way back out. Meanwhile, the most important present-day headline didn't come from a telescope image at all. It came from a laboratory-grade chemical analysis. In June 2026, a team led by Martin Cordner at NASA's Goddard Space Flight Center, publishing in the journal Nature, this is a direct chemical readout, and it says this object is nearly as old as the galaxy that made it. That finding lines up with something else researchers had already suspected from a completely different direction. Independent teams tracing 3I Atlas's path backward through the galaxy, including a group from Oxford using a statistical approach called the Otauta-High Oxford model, had calculated that its motion matches stars belonging to the Milky Way's thick disk, an ancient population that formed long before the thin, younger disk our own sun belongs to. Two completely different lines of evidence, one based on orbital mechanics and one based on isotope chemistry from Webb, converged on the same conclusion. 3I Atlas is not merely older than any comet ever studied up close. It is very likely older than the Sun, older than Earth, older than the solar system itself by billions of years. A genuine fossil from an era of the galaxy no instrument has ever sampled directly before. There is one exact date worth marking on a calendar, because it isn't a projection or an estimate. It is orbital mechanics, locked in by the same physics that governs everything from tides to satellite launches. In April 2027, 3I Atlas will cross the orbit of Uranus, continuing its outbound journey at the same roughly 61,000 km/h clip it carried on the way in, essentially unchanged by its brief pass through our solar system's inner neighborhood. A year after that, in 2028, it will cross the orbit of Neptune, the last major planetary boundary in the solar system, before heading out toward the distant, icy edge of the Oort cloud and, eventually, back into true interstellar space, never to return, never observable again, its brief and record-breaking visit reduced permanently to the data already collected. There is no ambiguity in that timeline. It is simply where the math says the object will be. Now, the part that hasn't fully resolved and deserves to be said plainly rather than buried. A small number of researchers, most visibly the Harvard astronomer Avi Loeb, have argued publicly that 3I Atlas displays a longer list of statistical oddities. Its retrograde orbit sitting unusually close to the plane of the planets, an unusual blue color near perihelion, a nickel to cyanide ratio in its gas plume that looks different from other comets. And Loeb has suggested some of these anomalies could, in principle, indicate something other than a natural object. That view remains a minority position within the astronomical community, and it's worth being honest about why. The vast majority of researchers studying 3I Atlas, including the teams behind the Rubin Observatory photometry and the Webb isotope analysis, find its behavior consistent with a natural, if genuinely unusual, ancient comet. Its trajectory shifts, explained by ordinary, if vigorous, outgassing and its chemical oddities, explained by the simple fact that it formed somewhere our solar system never has direct samples from. Both sides of that debate agree on far more than headlines suggest. This is a real interstellar visitor. It poses no threat to Earth, and its unusual properties are exactly the kind of things scientists hoped an object like this might eventually reveal. Where they disagree is on how much weight to put on statistically unlikely coincidences before defaulting to the simplest explanation. That disagreement hasn't been resolved by a single new dataset, and it may not be, now that the object is already on its way out of range. Zoom out from the isotopes and the orbital mechanics for a moment, and there's a bigger pattern worth sitting with. For most of human history, understanding what lies beyond our own solar system meant looking outward through a telescope and doing math on light that left its source years or centuries ago. Inference stacked on inference, never a direct sample in hand. 3I Atlas represents something categorically different, a piece of another star system's actual leftover material arriving on our doorstep, on its own schedule, requiring nothing from us but the patience and the instrumentation to be ready. That readiness wasn't an accident. It was the product of decades of unglamorous investment in survey telescopes built to watch empty sky for years waiting for something to move. In space, telescopes designed to squeeze isotope ratios out of gas 100 million kilometers away. In international coordination, good enough to keep tracking an object even when it vanished behind the sun. The story of 3I Atlas isn't really about one comet. It's about what happens when a species finally builds the tools patient enough to notice something that was always happening around it, constantly, invisibly. For as long as there have been stars flinging debris into the dark between them. Consider, too, what it means that this is only the third confirmed interstellar object, discovered just 8 years after the first. Rubin Observatory's full 10-year survey has barely begun, and researchers who study the statistics of these encounters already expected to catch far more objects like this one, potentially dozens over the coming decade, each one a fresh, uncontaminated sample from somewhere else in the galaxy. That means 3I Atlas is not the end of this story. It's closer to the opening chapter of an entirely new branch of astronomy, one where humanity no longer has to choose between building an interstellar probe or waiting patiently for centuries. It simply has to keep watching, because the galaxy, it turns out, has been mailing us samples all along. We just didn't have the eyes to see them arriving until now. There is an image worth holding on to after all the numbers fade. Somewhere out past Jupiter right now, tumbling outward at 61,000 kilometers an hour, is a chunk of ice and rock that finished forming before our own sun was even a diffuse cloud of gas, a fragment of a planetary system that may no longer exist, carrying a chemical memory of conditions in the galaxy that no living star has experienced in billions of years. It briefly grazed the light and warmth of a star that isn't its own, shed a little of itself into a tail visible from a small backyard telescope, and then kept moving. Indifferent toward a darkness it has already spent most of cosmic history inside. It did not come here for us. It will never come back. And for a handful of months in 2025 and 2026, it let two of the most sophisticated instruments humanity has ever built look directly at it and read its age off its own atoms, like a name carved somewhere nobody thought to check until now. So here's everything in one breath. 3I Atlas was discovered on July 1st, 2025 by the Atlas Survey, but Vera Rubin Observatory had unknowingly photographed it 10 days earlier, during its very first night of testing. Hubble and Webb found it chemically unlike solar system comets, rich in carbon dioxide and later showing the first ever direct detection of methane gas in an interstellar object. Its perihelion passage in October 2025 happened almost entirely hidden behind the sun, sparking real scientific tension over whether it would survive intact. It did, and post-perihelion data confirmed its trajectory shifts matched ordinary cometary outgassing. In June 2026, Webb's isotope measurements, backed by independent orbital modeling, placed its formation at roughly 12 billion years ago, likely making it older than the sun itself. If a story like this, where real telescopes, real data, no invented drama, is the kind of space coverage you want more of, subscribe and turn on notifications, because the next confirmed interstellar object Rubin's full 10-year survey catches is likely only a matter of time, and I'll be covering it the moment the data is real. Here's the question I actually want to know your answer to. Does an object this old, this indifferent to us, make you feel smaller? Or does it make the fact that we caught it at all feel like the biggest win humanity's had in years? Let me know in the comments. I read every single one.